Okay, another counter model is a 3-bit out of order counter. As you can see, the sequences, they are not in an order, they are going in a random way. So let's draw the state diagram first. 0, 0, 0. It's not necessary, but let's draw it. 1, 0, 0, and 1, 1, 1, and 0, 1, 0, 0, 1, 1, and it goes back. So it's not covering all of it, but there are some missing states in between, but we have to consider them as well. So in total, we have got 1, 2, 3, 4, 5 states. So this is a 3-bit out of order counter. Based on this, we have to derive our state table. So as we have got 5 states, 5 state means we have to use at least 3 flip-flops in order to cover all possible states. So A, B, C. Again, there are no inputs, no outputs over here. So A plus, B plus, C plus. And starting from 0, 0 up to 1, 1, 1, we have to consider all possible combinations. Let's write these closer to each other because I have to add a few other things. Okay. So the present states and the next states are given. So when we are in 0, 0, 0, next state is 1, 0, 0. Then 0, 0, 1 is not used, so it said don't care. A new state. 0, 1, 0 to 0, 1, 1. 0, 1, 1 to go back to 0, 0, 0. And 1, 0, 0 goes to 1, 1, 1. And 1, 0, 1, it's also unused. 1, 1, 0, it's also unused. And 1, 1, 1 goes to 0, 1, 0. So here are the present states and the next states. Now, when we want to implement these, as it didn't specify, we can again use the type flip-flop. We just need to highlight, take each of the next states as they're equals to the flip-flop inputs, and we can just generate the k-maps and find it out. But rather than doing that, I'll use JK, but from the slides, let's go through the type flip-flop implementation. So each of the states, next states, A, B, and C, as you can see, the k-maps can be derived, extracted from the state table, which they are going to give us the flip-flop inputs for D-type flip-flop, if we use D-type flip-flop. So next states, as for output follows input, that means DA is going to be whatever the QA is. So we can cover those 4 over there. So A is changing, it is just B prime. And DB is, we can have these 2, which is A and C. And DC is, we can have these 2 and these 2. So A and B prime or B, C prime. So we can have these statements. There is another one over here, so that has to be covered. And we can have the flip-flop inputs, then we can generate the circuit required. So the circuit is as follows. This is a D-type implementation, which we just have 3 flip-flops, 3 inputs, which they can be derived from the next states. And now as we don't have some of these states and they are unused, what will happen if we end up in an unused state? So machine checks, and then if it gets into those unused states, in the next clock it will jump to the next upper state so that it can recover. So for example, 001 will go to 010, and 101 can jump to 111, and so on. Okay, so most closed defined state they will jump to. Okay, so if we want to implement this 3-bit out of order counter with JK, so this is what I'm interested now. And before we get into the JK, the state table, let's remember what was JK's properties. So the next state equation is J Q prime or K prime Q. You can derive this if you don't remember it. Now, in our truth table or state table, we have seen that we can use 4 different states with JK flip-flops. And what are those states? When it is 0, 0, it just holds the previous value, so it's 0, 1. When it is 0, 1, it's a reset state, so output resets. 1, 0, it's a set state, so the output sets. And 1, 1, it's an invert or toggle state. When it is 0, it will be 1. When it is 1, it will be 0, as both are 1. So this was the characteristic table of JK, which we can derive this equation. And JK flip-flop also has excitation table. Now in the excitation table, we have to have present state, next state, J and K. So we have to observe how the present and next is excited, so the inputs are changing. 1, 0 and 1, 1. Now, we have to be really careful here because we are going to use both of them. This is known as excitation. Okay, so let's look at the first one. The present state is 0, next is 0. Now, when we say both are 0, either we are holding, because either it's this one, it holds, or it is resetting in any of these, okay? Because the next states are zeros over here. So when we look at J, it's always 0. K is changing from 0 to 1. So we can say that J is 0, K is don't care, is changing. Then we look at 0, 1. So the present is 0, next is 1. There's only 2 choices again. Either we are setting, okay, so in both cases it's going to give you 1, or it's just a complement because the present is 0, next is 1. Okay, so in those cases, as you can see, J is 1, but K is changing. So 1 and X. Then we go for the next one. It's 1, 0. So present is 1, next is 0. Either we are resetting, it's again this one, or we are taking the complement, or this one. So J is 0 and then changes to 1. K is always 1 in these cases. So then J is don't care, K is 1. And the last one, when both are 1, either we are setting again, setting to be 1, or it's just the complement. It's hold. Okay, so in those cases, if we are setting or holding, J is 0, then it is 1. k is 0, stays 0. So we can say x and 0, and that's the excitation table for JK flip-flop. Now we are going to use this information, the excitation table, so that we can derive the state table required over here. Now, what do we need? We need to have JA, KA, JB, KB, and JC, KC. Okay, so I'll just put excitation table here as well, just to make sure that we do remember what we are doing. 0, 0, 0, 1, 1, 0, 1, 1. And we know that 0x, 1x, x1, and x0. 0x, 1x, x1, and x0. Okay, so let's start with JA. JA and KA. So 0, 1. So 0, 1 means 1x. 1x. XX, these are don't cares. So I'm just putting don't cares. 0, 0 is 0x. 0, 0, it's also 0x. 1, 1 is x0. And 1, 0, it's x1. Then I repeat for JB. 0, 0, it's 0x. These are don't cares. Then 1, 1 is x0. 1, 0 is x1. And 0, 1 is 1x. And 1, 1 is also x0. And we have got the JB from here. And we have to repeat the same thing for JC as well. So let's start with the don't care ones, because these are going to be don't cares. So 0, 0, it's 0x. 0, 1 is 1x. 1, 0 is x1. 0, 1 is 1x. And 1, 0, it is x1. So we have got the state table as it is required in order to derive the flip-flop inputs. Okay, so let's go from the slides as well. We are going to use JK as we already done it over here. That's the characteristic table and the excitation table that we already derived from the characteristic table. You can easily how the present and next is changing and how they are affected by the inputs, or how the inputs are actually affected from these excitation. And we have got the excitation table. Then the similar table that we have already derived can be found here as well. So 1x, don't cares, 0x, 0x, x0, don't care, x1. And then we have got 0x, don't care, that should be x0, then x1, 1x, don't care, x0. Then we have got 0x, don't care, 1x, x1, 1x, don't care, and x1. So you can see that we have got the similar table. Now, next thing that we need to do is derive the K-maps. So we need 6 K-maps, as we have got JA-KA, JB-KB, and JC-KC. So this is for JA. I'll write JA over here, and this is for KA. Then we need it for JB, KB, ABC, ABC, 00011110, 00011110, 01 and 01. This is KB, sorry, JB and KB. And then we just need to repeat the same thing for JC and KC. Zero 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 one 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 zero zero one 00011110. Okay, let's plot those. And 1x 0 0. So 1x 0 0. And then rest are all x's. Then k is xxx, 4 x's. And then 0x x1. Then jb 0x x and x. Then 1 x x and x. Then KB is x, x, 0, 1. And then we have got x, 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 0. Then JC is 0x, 1x, and 1xxx. Then KC, 3 x's and 1. And then 3 x's and 1. So let's start combining largest possible. So this one, those 4, where we have got A is changing, is just B prime, and KA is, we can have the centers, which is going to be C. Then JB, we can have those 4, which is going to be A, and KB is, we can just have those 2, which is A prime C. Then JC, it is B, or those 4, which is A. And KC is, we can combine all these together, which will have 1. So we have got all the flip-flop inputs. We know what they are now, and we can just implement the circuitry. So I'll rewrite those. JA is B prime and KA is C. JB is A and KB is A prime C. JC, B A plus B, and KC is just 1. So we have got all the flip-flop inputs. All we need to do is implement the circuitry. We need 3 JK flip-flops. That's 1, that's 2, and that's the third one. So JK inputs. Q, Q prime, Q, Q prime, Q, Q prime. Now JA is B prime. Let's say this is A, this is B, and this is C. JA is just B prime, so I'll get B prime from here and fit in. KA is C, so KA is C. Then JB is A, so A is coming from here. Fit it into JB. KB is A prime C, so there's an AND gate. A prime and C, which is this one. And then JC is A plus B, so I need an OR gate. A plus B, and KC is just 1. And that is the implementation of the 3-bit out of order counter using JK flip-flops. You can see the K-maps that we have derived and circuitry. We can also implement the same function with T-type flip-flops like we have done with the counter example before. So excitation table is similar with the characteristic table for the T-type flip-flop, if you do remember. And so 0, 1, that means T has to be 1, it's toggling, don't care, not toggling, not toggling, 1, 1, not toggling, don't care, and 1, 0 toggles. Then 0, 0, not toggling, don't care, 1, 1, not toggling, 1, 0 toggles, 0, 1 toggles, don't care, and 1, 0, 1, 1 also not toggling. So 0, 0, not toggling, don't care, 0, 1 toggles, 1, 0 toggles, 0, 1 toggles, don't care, and 1, 0 toggles as well. And again, we have to extract TA, TB, and TC to the K-maps. So these are the K-map representations for each of the flip-flop inputs. We can combine A prime and B prime, or A and B. This is like an XNOR. And TB is A prime and C, and this is A, B prime. And TC is, we can have these four, which is B, and we can have these four, which is A. So A or B can also be used. So that's all we need to know about sequential circuit design. There are a few exercises in the end. We will solve those during the live lectures. Thank you.